Hi everyone, thank you for joining. This is Congcong Liu from JD.com. Today I'm gonna present our work, Generative Contextual Comprehension Paradigm for Takeout ranking model done at JD.com. The core idea is to frame Takeout advertising ranking. Instead of a set of fragmented feature classification modules, we model it as a single contextual comprehension task in one generative architecture. I will walk through why Takeout ranking is hard, how GCRank decomposes and models context, and the offline and the online results. Let me start with the background. Ranking is the central stage of the advertising system. It governs platform revenue through eCPM and shapes user experience, so it sits at the balance point between the two. In Takeout, three properties make it especially hard. First, spatial temporal constraints. Delivery distance and preparation time are strict, so the model must understand the geography and the timing. Second, contextual preference differences. The same user wants different things in an office district at noon versus a residential area at dinner. Third, AOI level characteristics. A business district and a university town drive different consumption patterns. Traditional models struggle to capture these dynamic intertwined signals together, which limit how well they read user intent. Here are the limitations of existing methods. Traditional models rely heavily on handcrafted feature engineering, and their modules are optimized in isolation, so the system never forms a unified understanding of the full context. Existing generative models help, but they lack systematic modeling of multidimensional context, especially spatial temporal dynamics. Prior LBS works, such as OneLog, focuses on geographical proximity, which is not enough for the richer interactions in Takeout. So there is a clear gap. We need one generative framework that integrates the different contextual dimensions and read complex user intent in a unified way. This is the paradigm we propose. We treat ranking as contextual comprehension, and we decompose the environment of the user request into four complementary dimensions. Static context covers slowly changing signals like user demographics, basic store attributes, and constants like season. Dynamic context covers fast-changing signals parsed at request time, like the exact hour, real-time weather, and current delivery capacity. Personalized context is the user's historical interaction sequence. Each interaction tagged with the situation it happening in. Collective context captures group level and AOI level patterns, such as regional taste preferences. So GCRank models each of these dimensions and importantly, the relationships among them. This slide gives overall architectures. GCRank has two core components. The first is a generative takeout context encoder, the GCE with three specialized pipelines, the DCE for real-time situational reasoning using an LM and knowledge base, the CCE for AOI-aware collective patterns, and the PCE for personalized interest. The second is the Generative Context Fusion module, the GCF. It uses a low-rank parameter-efficient transformation to project the heterogeneous context tokens into a shared semantic space, reducing redundancy while preserving the task target. Together, they form one unified generative ranking pipeline. I will now go through each encoder module. First, the Dynamic Context Enhancer, the DCE. It handles the most volatile signals like time, location, weather, and immediate demand. We build a knowledge base from recent logs where each context maps to a structured snippet and a pre-computed LM embedding. At the same time, we embed the request context and match it against the base by similarity. If a similar context already exists above the threshold, we will reuse the cached embedding and skip LM inference. If it's a code context with no good match, we trigger asynchronous LM reasoning to generate a fresh representation and add it to the base, which is also refreshed weekly. So this keeps the module expressive and fast enough for production. Next, the Collective Context Enhancer, the CCE. It mines group-level preferences and regional chains. We fine-tune the LM at AOI granularity. For each AOI, we aggregate about 60 days of click sequences from its stores, supervised with collective labels such as taste preferences, consumption levels, and demographics. The fine-tuned model then generates representations at multiple granularities, including store level, AOI level, and user level profiles that combines the stores user clicked, weighted between stores with specific and AOI-aware signals by the hyperparameter beta. That weighting gives robust coverage even for cold or sparse users across different zones. Now the personalized context enhancer, the PCE, it has two branches. The global branch processes the user's long-term behavior sequence with a transformer decoder using target attention against the candidate ad, given a stable long-term profile. The instant branch handles fine-grained spatial-temporal preferences where data is sparse. Rather than co-occurrence statistics, we formulate instant interest as a distribution transformation using flow matching. We start from the user's average historical interest and transform it toward the context-specific interest, guided by an embedding of the precise time and the location. We use the last historical interaction as a training target and adopt a mean flow strategy for efficient inference. The two branches are then concatenated. This is a fusion module, the GCF. Its job is to integrate the four heterogeneous context representations into one unified feature space. The mechanism has two parts. First, LoRa-based alignment transforms each context embedding into a shared semantic domain parameter efficiently. Second, the aligned embeddings are concatenated and pass through an MLP for deep interaction. The motivation is to maximize the mutual information between the fused feature and the target, while the low-rank constraint reduces redundancy and the MLP captures cross-context synergies. This produced a unified discriminative feature used for the final ranking score. Let me turn to the experiments part. Our dataset comes from real JD Takeout logs with over 2 billion samples and rich textual attributes. We compare against the traditional baselines like DNN, DIN, same for long behavior sequences, against generative baselines like HSTU and OneLog, the SORTA LBS generative model, and against our heavily optimized production DLIM, a strong industrial benchmark. On the model side, the CCE backbone is Qwen 1.5, 0.5 billion model. The DCE used DeepSeek R1 for reasoning. These are the overall results. GCRank reaches the best AUC across all baselines by a clear margin. OneLog, which models geography alone, underperforms here because Takeout needs temporal dynamics and group preferences modeled together, not spatial proximity in isolation. Most importantly, GCRank also beats our production DLIM, which has been optimized over many runs. That supports the central point. A generative model that integrates multiple contextual dimensions is a viable, strong approach for industrial ranking. This slide decouples the contributions through ablation, averaged over 5 runs. Removing any single module degrades both CTR and CVR, which confirms every component does real work. The largest drop comes from removing the DCE and the CCE, with CVR falling about 7.5 and 6.5% in relative terms. So the dynamic and collective dimensions matter most in food delivery. On hyperparameters for the PCE flow matching component, classifier-free guidance is best at a scale at 2.0, and the large normal time sampler gives smoother gradients and outperforms uniform linear schedules. Beyond offline metrics, we ran a 7-day online test on the production platforms with 20% of the traffic. against a highly optimized production base. GCRank deliver clear gains. The deployment used 3 pipelines, 1 inherited real-time serving pipeline plus 2 generative pipelines that update and serve the DCE and CCE. And despite that, the serving cost is more. So the framework adds meaningful value at an acceptable cost. That concludes the talk. To recap, GCRank reframes takeout ranking as contextual comprehension, decomposes context into static, dynamic, personalized, and collective dimensions. Model each with a specialized module inside the GCE and fuse them with the GCF. It achieves sort-of offline performance and significant online gains. Since this is a recorded talk, so if you have any further questions, we would be glad to hear from you by email at the addresses shown on this slide. Thank you for your time.